Okay, in previous week, okay, we have get a expression for magnetic vector potential. Okay, magnetic vector potential, that is ART. Okay, so that is a function of position and both time and position. Okay, so this is called a wave vector. Okay, so last time we get a solution for this magnetic vector potential. Okay, potential uh, at some distance from a current density, volume of a current density. Can you remember that? Okay. So, so this is related with position. Okay. So we have to use a coordinate system to give the position. Okay. So this is Z, this is Y, and this is X, correct? Okay. X, Y, Z. Okay. Okay. So, uh, so if we think that if we have a current density here, okay, current density here, that is J. Okay, J is the current density. Okay, J is the current density. Okay, and uh, so if you consider this, this is the distance from 0 to the J. Let's say that it is R dash. Okay, so here it is get R dash now. Okay, R dash. Okay, and this is the current density. Okay, so we consider a volume of current density. Okay, okay, and so if you want to get a vector magnetic vector potential at any point, okay, in the space, free space. Okay, so you can take any point. Okay, this is an arbitrary point, any point. Okay, and let's say that that position vector is the R. Okay, okay, and this R dash actually the position vector of this point, and this R is the position vector of this point. Okay, and so we need to find the magnetic vector potential of this point due to this current density. Okay, so it is like this. Okay, so here we get, okay, and okay, let's say that this is n. Okay, so this is the vector between J and this point. Okay, so if you consider this as R, okay, this as R, okay, so this R is a vector, no? It has a direction and magnitude. Okay, so R is equal to, so you can use the basic vector law. Okay, so you know that R equal to dash plus R equal to R dash, no? Okay, so you can get R is equal to position vector of this point, R dash, minus position vector of this point. Okay, minus R bar dash. Correct? Okay. Okay. So so this is the vector R. Okay. So if you want to get the distance between this point, this current density and the measured point. Okay. So this is the measured point. Okay. So if you want to get the distance, you need to get the magnitude, no? That is the R magnitude distance. Okay. So this is it. Okay. And okay, so we have seen that, okay, the magnetic potential of this point due to this current density is equal to this one. Okay, you not, okay, you no need to remember these things. Okay, and this is we consider a current density volume here. Okay, so we have to do a volume integral. Okay, so here V, okay, and J, this is the current density, and the current density also a function of position and time. Okay. Current density has a position, and also it is changing with the time. Current is changing with the time. Okay, and the current has a position also. Okay, so it is both it is a function of both position and time. Okay, and here it is t. Okay, so this t minus r by c. Okay, and this is divided by r, and you have to do a volume integral. Okay, because we are using a current density volume. Okay, so you have to do a uh, volume integral. Okay, and so okay, so what is this? Can you remember this part? In signal and system, maybe you have this. You have learned this. Can you remember? This is T minus RC. Can you remember that we are doing some time transformation technique? Time transformation technique. So here we are going to give delay and advance of time. Okay, and the time transformation. Can you remember that? You should have learned this in signal and system. Okay, so this is called actually time shifting. Time shifting. Okay, time shifting. And so in time shifting, you have a time and you can shift it by some another point. Okay, so if you get this is a delay. If you get plus b plus 2, this is a time advance. Okay, so the time axis is shifting here. Okay, so please try to remember these things if you need. Okay, okay, and also there are other time transformation techniques. Time scaling. Can you remember that? It is, you are going to multiply the time with the parameter. Time scale. So based on the value of this parameter, time can be expand or time can be shrink. Okay, like this. Time span can be expand or time span can be compressed like this, shrink like this. Okay. So actually here also time transformation is there. Okay. So here t minus r. So this is a delay. Okay. So how this delay happen? Do you have idea? So this is a wave, no? Here you are going to find the magnetic vector potential here. Okay. So how this delay is introduced? So you can see that this is c. C is the velocity of light, electromagnetic wave. Okay, this r is the distance. Okay, so if you divided r by so you know that velocity is equal to distance divided by t. Okay, time. Okay, okay, time. I will put it p. Okay, so if you get v divided by r, what is that? That is a time. No, you get the time. What is that time? Actually, it is a propagation time. Okay, because this wave should be traveled from here to here. Okay, so it is not instantly generated. Okay, as I can remember, it is called the fields are retarded. Okay, that is the word. You can see that radiated fields are retarded. Okay, can't instantaneously create. Okay, there is a propagation time. Okay, because it is traveling. Okay, so these fields are traveling actually. Okay, it is not so these are retarded. Okay, okay, it is called retarded. Okay, so so that this r by c is the propagation time. Actually here the propagation time, r divided by c means the propagation time, propagation delay. Okay, propagation delay. Okay, did you get that? Okay, so this is a propagation delay. Okay, so this understanding is important. Okay, no need to remember this. Okay, okay, now okay, now so we have this solution. We have this solution. Okay, we have this solution. Okay, we have this solution. Now we need to so you can see that here we have a position and time variation also, position and time variation. Okay, now we so it is somewhat complicated. Okay, because we have two variables here. This A is a function of time and position. Okay. So we need to, so there is a way we can eliminate this time part. Okay. So how, do you have idea how we can eliminate that? Okay. Yeah, we can have a transfer. Okay. We can have a transform. Okay. So signals or wave can be transformed into many domains. You know that. Okay. For example, if you consider a signal, okay, if you consider a signal can be transformed into time domain, signal can be transformed into the frequency domain, and also signal can be transferred into the phase domain, sorry, S domain, Laplace domain, complex domain, SOZ, okay, Laplace transform or Z transform, okay. So this is normally continuous signal we will have Laplace transform. For discrete signal, we will have the Z transform. Okay. So signal can be transformed into another domain for the analytical purpose. Okay, to make analytical easy. Okay, so we can do that transform. Okay, but for us, this transformation is the difficult one, no? But we use this transform actually to make the analysis easy. Okay, okay, because this we can get this transform very easy using a tool or something, using a software tool maybe. You can get this. You can calculate this. Okay, or using algorithm, you can calculate. Okay, so what I want to tell you is that so these are the normally we have we have we have we have studied this domain. Okay, and there is another basic domain that is called phasor domain. Okay, but phasor domain transform we don't learn that. Give me a moment. Okay, please. Hello. Oh, good morning. Oh, පුළන් පුළන් 12ටනේ දාලා දෙන්නේ. Right. හරි හරි. Okay. හරි. Thank you. Okay. So it is very simple domain actually. Phasor domain. We call phasor domain. Okay. So I will tell you. Okay. So if you consider this one, let's say that this is A cos omega t plus 5. Okay. If I write this like this, real of E j omega t. Okay. Let's eliminate this 5. Okay. If I write this, is it true or wrong? Can you confirm that this? One. Yeah. No, this if I write this like this, A cos omega t is equal to real part of E j omega t. Is it true? How can you say true? What is the formula? Can you remember that? In maths, you have learned this. No, Euler formula. Can you remember that? Euler formula. What is Euler formula? Euler formula said that E j omega t is equal to cos omega t plus j sin omega t. Okay. And also E minus j omega t is equal to cos omega t minus j sin omega t. This is the Euler formula. Okay. Euler formula we use in signal and system. Can you remember that? I think we are using this Euler formula several, very thoroughly in signal and system to find the Fourier transform or Fourier series of sinusoidal system. Okay. Because there is an exponential Fourier series of Fourier transform, exponential. Okay. So here, there we use Ej omega t terms. Okay. So if you can write your cos term and sin term with respect to Ej omega t, so there is an integral, no? When you are finding the Fourier transform or Fourier series, you have to do an integral, no? So that integral will be easy. Okay. So you are using this in signal and system. Didn't you use this? Yes. Huh? Yes, sir. Use now? Yeah. Who done the signal and system? Okay. Okay. Anyway, it is okay. Okay. But this should be used. Okay. Okay. So you can see that if you want to get, if you want to, if you want to uh, eliminate this sign terms, okay, you can add these two. Okay. So you can use you can write cost term with respect to this e terms. Okay. And also if you want to eliminate cost term, you can subtract. Okay. Then you can write sine omega t in terms of this exponential terms. Okay. So you can do the both. Okay. So what is this mean? A cos omega t is equal to, actually here there should be a should be come to here. Okay. Okay. So this is ej omega t. Okay. So if I multiply it by a. Okay. So this will be multiplied by a and this will be multiplied by a. Okay. And but you need to get this one. Okay. So this ej omega t is what? It is a complex value. Okay. It is a complex number. Okay. So this is the real part and this is the imaginary part. Okay. And imaginary part you have a sine theta, sine term. Okay. And if you get only the real part, you can get this cos plus. Okay. So if you get the real term of a e j omega t, what it is equal to what? Equal to a cos omega t. Clear? Yes. Hmm? It's a mathematics. Okay. Simple mathematics. Yes, sir. Okay. Okay. So actually this is related with the phasor domain. Okay. This is also related with the phasor domain. Okay. And here, okay. And here, this, okay. So here we assume that, okay. So there are many assumptions we use, okay, for this, okay. So that means this E field and H field is not exactly correct, okay, because we are doing many assumptions actually, okay. Okay. So this is our solution for unbounded free space, okay. This is our solution for unbounded free space. Solution for unbounded free space. Okay. And we assume that, okay, this time variation is sinusoidal. Okay. So this is sinusoidal. Sinusoidal means it is like this. Cos. Okay. So this time variation also related with the cos term. Okay. Sinusoidal. Okay. And you know that normal electromagnetic waves are sinusoidal in nature. Okay. That is the normal way. Okay. Those are sinusoidal in nature. Okay. So that assumption is somewhat correct. Okay. So you can assume like this. Okay. So if you assume like this, okay, you assume like this, okay, and this can be right like this one, okay, in this way. Okay. So this solution can be right in phasor domain like this, okay. So if I write it here, you no need to remember that, okay, but you should have the idea. So you can, so we have a solution for RT, no? Okay. Yes. So same thing you can write for, so you consider this R is a sinusoidal variable, okay. So you can write it as like this, R dash real of E J, okay. You can, yeah, real of ej omega t like this, okay. And you can put this one also here, okay? Because this film doesn't have any no, I think the correct way is you have to write it inside this, okay. Real of ar ej omega t, okay. And this is, okay, this in this way, okay. So we get the real of ar ej omega t, okay, like this, okay, as we see here, okay. And this is equal to the solution, okay, solution like this, okay. We have found it, previously. There is integral, okay, and that solution, okay, so you can get the real parts, okay, you have to find the real parts here, okay, then you have to divided it by ej omega t, okay, then you can get this solution in phasor domain as, okay, like this, okay. Mu naught 4, 5. The volume integral is still there. JR. Now the time is not here. Okay. This JR is also converted to the phasor domain. Okay. This JR. This is also a time and position and time dependent variable. No, this J. Okay. It is a function of both time and position. Okay. So this time also converted in, so that's J is also converted into the phasor domain. Okay. So at the phasor domain, we don't have the time variable. Okay. Only the position variable is there. Okay. So we will have this E minus JK R divided by R dV dash. Okay. So you will have this one. Okay. You will have this one. And here the K is, okay. And here the K is omega divided by C. Okay. And this is called the wave number. Okay. So here, oh, but lecture. Come on again. What do you know? Yeah. My kai hatali annan kela beli. Okay. So this K is equal to omega by C. Okay. So this C is the velocity. Okay. Okay. C is the velocity. And this omega is the frequency. This one. Okay. This omega is the frequency of the signal, RF signal. Okay. 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 So, so this is the, so we can get that solution into phasor domain like this. Okay. So this is the phasor domain representation of the magnetic vector potential, and we don't see the time parameters is here. Okay. So time is eliminated here. Okay. So we get only a one variable, the only a one variable function. Okay. Okay. So it is a function of position only now. Okay. Okay. Now, okay. So now, okay. So first we are going to learn about the wire antenna. Okay. Wire antenna. Okay. So if you are considering the wire antenna, we have several wire antennas. Okay. Okay. Wire antennas. Okay. So the wire antenna, I think you can remember that it is come under element antenna. Okay. Only one element is there. Is to transmit. Okay. So that is our first part one. We have learned this. Okay. So, so this is a type of element antenna, wire antenna. And in wire antenna, the most popular one are monopole and dipole. Okay. Monopole and dipole. But we have other types also, infinitely small, and I can't remember the name, actually names. Okay. Infinitely small dipole, okay, and small dipole likewise. Okay, so there are many. Okay. So these are wire. Okay, actually wire. Okay, but here we consider current density. Okay, here we consider current density, volume current density. Okay, and if you use a wire, it is just a wire. It is a line. No, it is a line. Okay, so if you consider a wire, okay, now look at this one. Okay, okay, now we are using this one. Okay, phasor domain representation of the magnetic vector potential. Okay, so what is the things we have done? First, we have find the magnetic vector potential equation. Second, we have find the solution for the unbounded free space. Then we find the phasor diagram of the phasor representation of the solution of that solution. Okay, for free space. Okay, now we consider a line current. Okay, we consider a line current. Okay, so the so if I consider the coordinate system like this, z y x. Okay, let's say that this car the line is like this. This is a wire. Okay, and a current is going through this. Okay, and if the current is going through this current should be changed. No, otherwise it will not create the E field and H field. It will not create the electromagnetic field. So this current is a function of time. Okay, and if you consider this position, any position of this line, okay, you have to find a position. Okay, and at this position there is a current density. Okay, at this position there is a current density, and that current is changing with the time. So this current density also changing with the time. Okay, and this you get any position, no? So by position, if you take different position, this current density may be changed. Okay. So this current density again, if you consider line current, this current density is again a function. Okay, okay, current density of a line current density of a line, density of a wire. Okay, wire. Okay, and you can consider this as antenna. And here also, if you consider this as antenna, this volume is antenna. Okay. So that is the so we have found the magnetic vector potential due to this antenna. Okay, and here our wire is now antenna. Okay, and we are considering a position. Okay, we are considering a position. Okay, and the current density of a wire, okay, of this wire, of this wire change, okay, change with respect to time and with respect to position. Okay, let's say that it is r dash position. Okay, so this j is also a function of r dash and t. Okay, if you consider line form. Okay, but now we didn't consider the time variation because it is a sinusoidal. We consider it as a sinusoidal variation, and we get the phasor domain representation. Now this density we can consider as a function of position only. Okay. Now you want to find the current density. Okay, you want to find the current density. No, you want to find the magnetic vector potential due to this current density at any point. Okay. So in the same way, you can consider this as the r dash, this point. Okay, like previously we get. Okay, and this point you can get as the r dash position. Okay, and there is a position vector like this. Okay, like this, like this. Okay, and so this is the one. Okay, this is the one. Okay, and okay, so I get this. So there is a so from here to here there is a position vector. Okay, and I take that position vector as n. Okay, so we have three position vector: r dash, r bar, r dash bar. That is the position vector of the current density, and the position vector of this magnetic vector potential. Okay, so we have these things. Okay, okay. Now you can get this. You can transform this. This is a volume. This is the solution for the current volume, current density volume. Okay, but here it is a line. Okay, and so this you have this one. Okay, you have this one r dash is equal to. So this is a volume integral now. So because this is a line, this volume integral become a line integral. Okay. So we have, finally we have this one, mu naught for 5. Okay. So this is a line. Okay. So it should be a line. Okay, not a volume, because this is a line. Okay. So this volume become a line. Okay. So we have L. Okay. And we have the others are same. Okay. Yeah. And another thing is, okay. So, so you consider this as a very thin wire. Okay. Very thin wire. Okay. So there is no density actually. We didn't consider a density. We just take it as a current. Okay. So there is no current. The current will become, sorry, density, current density will become simply a current. Okay. And it is, okay. So here the J is not here. This J become current. Okay. And it is just a current with respect to the position. Okay. With respect to the position. Okay. And here we have that current. Okay. Dash. Okay. E minus JKR. Okay. Divided by R. Okay. And so this is become this volume also. This volume also will become a line integral. Okay. DL dash. Okay. So for a line current, the solution will look like this. Okay. This is the solution for the magnetic vector potential in phasor domain for a line current. Okay. And our antenna is also line current, so you can use this one. Okay. And we have to do another assumption also. Okay. Another assumption, that is, if you consider antenna, if you consider antenna, okay, if you consider antenna, okay, maybe you have learned this. Okay, I can't remember the value. Okay, there. So this is the antenna. No, it is propagating. It is radiating or receiving. Okay, so if you consider near one, okay, so this is called near field of the antenna. This is the near field of the antenna, and beyond this one, we call the far field of the antenna. Okay, far field of the antenna. Okay. Let me give. Okay. So if you consider antenna, okay, if you consider any antenna, okay, consider any antenna, okay, maybe a monopole or dipole or something, okay. So if you consider any antenna, okay, like this, okay, okay. So we can define three regions with related to the antenna, okay. So one is we called, this is called a reactive near field, okay, reactive near field, reactive near field, okay, near field. That is very much close to the antenna, okay. So let's say that it is, we have a distance R1, okay, from the antenna, okay, and we can define another region, okay, like this, okay, okay, and let's say that is from the distance is R2, okay? And this region we called, okay, this region, okay, this region we called radiating near field, okay, radiating near field, okay. So this is reactive near field, okay. Actually here the reactive power is very large, okay. We will learn the power, okay, power and other things related to antenna, okay. So just have this idea, okay. And this is we called uh, radiating near field, radiating near field, okay. Okay, and there is a value for this R1 and R2, okay. For example, R1 is equal to 0.62, okay, D3 by lambda, okay. So this is the near field of the antenna, okay. And this D is the dimension of the antenna. This D is the dimension of the antenna. Okay, dimension of the antenna. Okay, of antenna. Okay, this D is the dimension of antenna. And if you can, if it is a dipole or monopole, that is the length. Okay, so this is the maximum dimension actually. So if it is a dipole or monopole, that is the length. Okay, so if it is maybe a half-page antenna, maybe the D is the area. Okay, like this. Okay. And the R2 can be defined as like this, 2D square by lambda. Okay, so lambda is the wavelength of the frequency you are using. Okay, so likewise you can define these regions. Okay, and beyond this R2 we call this a far field, radiating far field. Okay, radiating far field. Okay, and remember that our derivations, our derivations we do in the far field of the antenna. Okay, not the near field. These are the near field. And our derivation will be based on the far field of the antenna. Okay, actually we need the far field. Okay, because this near field, it can be changed, fluctuate. Okay, so it is hard to get a value. Okay, it is hard to derive the E field and H field in the near field. Okay, but we can derive the H field and E field in far field easy, more easy. Okay, so for any transmitting and receiving antenna, okay, so that is one thing you should remember. Okay, related with the antenna, any antenna that is transmit maybe and maybe receive. Okay, all derivation, all derivation, or all calculation. Okay, we done in this far field region. Okay, not the near field region. Okay, so if you consider antenna, okay, if you consider antenna, okay, so that is one thing you should remember. Okay, and if you consider antenna, there are many things. Okay, we can't learn everything. Okay, we will try to do that. Okay, anyhow. Okay, so so there's so you can use some assumption for the far field. Okay, far field means have some distance. Okay, so if you consider this one, okay, so if you consider this one, okay, I will write it here. Okay, I will try to write it more clearly here. Okay, so here you have the Z axis, here you have the Y axis, and here you have the X axis. Okay, and you have a line like this. Okay, like this. Okay, and you consider point. Okay, and this is you have R dash. Okay, and you have another point like this, and it is you have R dash. Okay, and this is R dash. Okay, and if you consider this one up to here, that position vector is N dash. Okay, that position vector is N dash. Okay, okay, and at the far field, that means this point is going to the far, very far. Okay, so you can assume that this one and this one is somewhat parallel. Okay, at the far field, you can assume that this line and this line is parallel. Okay, so at the far field, at the far field, uh, at the far field, you will get this kind of diagram. Okay, so this is our point. Okay, and this is the point. Okay, and this is like this. Okay, so this is the R dash. Okay, and this is R dash. Okay. So we are not, we don't need this parameter actually. Okay. We need the parameter, this one. Okay. So this is going to this one. Okay. Uh, but at the far field, you can consider that. So I'm going to draw this part. Okay. This part. Okay. This line. Okay. And that line is parallel to this one. Okay. So that is the assumption at the far field. Okay. So that is parallel to assumption, parallel to this line. Okay. Okay. So this R dash and N dash is parallel. Okay. R dash parallel to N dash. Okay. Like this. Okay. So this is the far field assumption. Okay. So by doing this assumption, you can derive this one. Okay. You can derive this one. Okay. At the far field, the magnetic potential vector potential is equal. Actually, not exactly equal. It is approximately equal because we are doing this assumption. Okay. This parallel assumption at the far field. Okay. So this AR, okay, the magnetic vector potential you will get as like this. Mu after I 4, 5 R e to the power minus jk r dash. Okay. Okay. Okay, you can consider, so you can consider this as a line or this as a volume. Okay. So here I write it with respect to the volume again. So it will be V J R dash, okay, e to the power J K N dash R dash, okay, dV dash. Okay. So you can get this value. Okay. So you can get this um, solution for the magnetic vector potential, okay, at the far field. Okay. And for a line current, okay, so for a line current, again, this V and this one become a line. Okay. Yeah, these are volume. Okay. So what I want to tell you is that this assumption is valid for the volume also. Okay. Not only the line. Okay. But here we consider the line. Okay. Because we are going to find the radiated field of line, the wire antenna. Okay. Wire antenna. So for a wire antenna, okay. So this is for a wire antenna line. Okay. For a wire antenna. Okay. For a wire antenna, we have this one. This is approximately equal. Okay. But I will put equal sign here. It is equal to mu naught e to the power minus jkr. Sorry. Jk simple r. Okay. jkr divided by 4, 5 r l. Okay. I r dash e to the power jk n dash r dash d. Okay. So this is, you have a line integral here for a wire antenna. Okay. So you need to keep remember this one. No need to remember, but you need to know how to apply this. Okay. So we will do some example. Okay. So you need to know how to apply this. No need to remember. Okay. This will be given, but you have to know how to apply it. So application is very simple. Okay. For a different current, what do you think? What is changing? What do you think? For different current, what will change? R dash. No, that is a position. No? For a different antenna. So if you consider a dipole antenna, okay. If you consider dipole, if you consider monopole, okay. If you consider Yagi antenna, infinite is small dipole, okay. So you can get position as a correct, no? For this one and this positions are same, okay. But what is the parameter related with the antenna, you think here? The far field. No. That is again position, no? It is a distance now you are going. So at far field mean you are going to measure the field at the distance. Okay, at the far distance, far away distance. Okay, so that is common for monopole, dipole, any antenna. Okay, and what is the parameters? Okay, uh, in this expression, you think that is unique to antenna. Just think. Okay, for antenna, what you are giving? You are giving a signal, no? For a sign, let's say that you want to transmit a sinusoidal signal through this antenna. You are feeding a signal to the antenna, no? Okay. So antenna will be transmit. Okay. So due to this signal, what parameters will be changed? That is, these will not change. These are normally these are constant. This K is also a constant. Okay. This R is not a constant, but for a dipole, any pole, you can consider this R. Okay. That is a specific distance. Okay. And what is the change in parameter? This current. Okay. So different antenna will have this different current distributions. Did you get it? Okay. So different antenna will have different current distribution. That is the key point you should keep remember. Current distribution. It has several current distribution. Okay. So if you consider two separate antenna, the current distribution will be changed in that. Okay, it is not same. Okay. So this current distribution, according to this current distribution, the antenna field also will be changed. Okay. Hello, Ushan. No, no. No, no, very correct. All right, very correct. Okay. Okay. So if I give you a current distribution of antenna, okay. If I give you a current distribution of antenna, you should be able to find the magnetic vector potential of that antenna in some point in the far field. Okay, so that should be you should be able to do that. Okay, and also using this parameter, this AR. Okay, using this magnetic vector potential, we can find the H field and E field of the antenna. Okay, H field and E field of the antenna. Okay, so I will give you, so this also can be derived using the vector identity. Okay, but we are not going to derive it. Okay, so you can, so you no need to remember this one. Okay, okay. So H field will be equal to JK. Okay, JK. This J is imaginary value. Okay, this J represent imaginary value. Okay, JK mu naught n dash n n multiply by a. Okay, so you can get this one H field. Okay, so you can consider, you can find the H field. Okay, and if you find the H field, you can find the E field also. E field will be equal to, these are approximately equal. Okay, approximation. Okay, this is 9 mu n dash multiplied by H. Okay, so you can find the H field and E field once you have find this magnetic vector potential. Okay, so you should be able to do that. Okay, so we have 10 minutes now. Okay, we will consider one example quickly. Okay, Okay, did you get it?
Yes, sir.
Okay, so what we need is this three. Okay, we need this three. Okay, and I will give you this derivation also. Okay, but you can refer for your knowledge. Okay, but no need the derivation. Okay, because this derivation is standard one. Okay, you can't do that derivation by use your knowledge. Okay, because you have to do many assumptions. Okay,
Finally, we need this equation.
yeah. Finally, we need three equations. Okay. So, um, so I want to, I actually, I explained the previous things. I want to tell you that we
Okay.
have a way to come to this solution. There is a way to come to this solution. Okay. And we have to do a lot of assumption, and we have to use a lot of vector uh, simplification, vector operation things. Okay. And we have to do some line and line volume surface integrals. Okay. So we can come to this one. Okay? But anyway, you no need to remember these three. Okay. But this will be given. Okay. If I give you the current density, you should be able to integrate it and find the magnetic vector. Then after that, you should be able to find the H field and E field. Okay. So we will do example and you can get more, so you can understand it clearly. Okay. Once we have done an example. Okay. So we will do an example. We have 10 minutes now. Okay. So, so that is it. Okay. So we will go to the example. Okay. So we will first find, we will try to find, okay. Actually, this H field and H field and E field are there. Okay. So after find this H field and E field, we can find many parameters, many important parameters related with the antenna. Actually, this H field and E field, these are important, okay, but these are not mentioned as antenna parameter, okay. But there are some antenna parameters like the polarization, like the half beam width polarization, okay, like that, okay, and maybe the internal resistance, okay. So normally those are mentioned, okay. So you know that the antenna are manufactured by many company, okay, like Comscope, okay, and what else? The company, can you remember? Do you know? Comscope and Andrew, okay. There's a company called Andrew. Maybe this is now Comscope. I can't remember, okay. But actually, when we are doing the mobile project, we like to get this antenna. Okay, so this is a very good antenna. Okay, it is standard antenna. Okay, so we like to use this kind of antenna. Okay, and antenna. Okay, so there are many specifications. Okay, there are many specifications related with the antenna. Okay. So H field and E field you can find like this. After finding the H field and E field, you can get many important parameter, other important parameter like half beam width, like polarization, like the internal resistance of the antenna. Okay, internal impedance, we normally refer it as impedance. Okay, and also the VSW are like this. Okay, so there are many parameters related with the antenna. Okay, but once we found this one, we can find. Okay, so we will try to find that one. Okay, so first we will try to find the magnetic vector potential and H field and E field of a wire antenna. So we get our first example. Okay, we will consider a infinite small antenna. Okay, infinite small dipole. Okay, so actually this has the most simple current distribution. Okay, because this is very so. Okay, so this has the simplest current distribution. Simplest current distribution. Okay, distribution. This has a simplest current distribution. Okay. And the infinite small dipole means the dipole length is very less than the lambda. Okay. So, for example, let's say that you are going to design an antenna for 2 gigahertz. Okay, 2 gigahertz. Okay, 2 gigahertz. Okay, then you can find using V equal F lambda. You know the V, that is 3 into the 10, 3 into 10 to the power 8 F lambda. Okay, so you know the F frequency, that is 2 gigahertz, and you can find the lambda. Okay, so let's say that you have find the lambda. Okay, and you take, so this is an lambda, you get some value. Okay, 5 centimeter value. So, but you take very short length, maybe 0.5 millimeter, some very short range. Okay, so that length is very less than the lambda. Okay, so that is called infinite small dipole. Okay, okay. So as I can remember, I'm not sure. Okay, I'm not sure about it. Okay, but I think um, that is this L. Okay, L is, if the L is less than lambda by 50. Okay, lambda by 50. If you divide lambda by 50 and your antenna length is less than that value, okay, that is the infinite small antenna. I'm not sure about this value. Okay, this 50 value, maybe it may be 100 or some, I'm sure. Okay, so anyway, if it is 50 means, let's say that you have lambda 5 cm, 5 centimeter. Okay, and if you divided it the lambda by 50, so you have 5 centimeter divided by 50 centimeter. Okay, so you have 0.1. Okay, 0.1 centimeter. Okay, that means 1 millimeter. Okay, so if you use 1 millimeter cable as the antenna, okay, it is an infinite small antenna. Correct? So you can see that this length is very small. Okay, because we are using very high frequency. The radio frequency is high at somewhat. Okay, so at high frequency, I also explain you that this it should be very high frequency. No, it is in radio frequency, right? Otherwise it will not propagate. Last lecture we have discussed it. Okay? So we should have somewhat high frequency to propagate it using antenna. Okay, and this L will be very small. Okay, and when the L will be very small, what happen is that, okay, if the L is very small, okay, uh, there is no any current distribution. Okay, there is no current change. Okay, we can assume like that. Okay, if the L is very small, if this L is very small, okay, we can assume that the current of the, okay, current of the uh, current of the antenna is uniform. Current distribution is uniform. Okay, that means if you consider antenna like this, okay, if you consider the current distribution here, and current here, current here, if you measure the current, this current are same. Okay, so this current is uniform. That is the idea. Okay? That is happened due to this L is very small. Okay, so there is no variation of the current through the antenna. There is no variation of the current through antenna. There is no variation. Okay. Through the antenna. Okay. Through the antenna. So we call this uniform current. It has a uniform current. Okay. So now you have to find the uh, you have to find the uh, A, magnetic vector potential. Okay. So we know that A is equal to magnetic vector potential equal to mu naught
Oh, yeah.
Ej. Yeah, I will write this as okay over 4 pi r
Integral.
integral. This should be L, no?
Line.
Okay, that means we are doing the integral through the line, through the line. Okay, L. Okay, okay, L. Okay, so you have this I r dash e to the power j k n hat r dash hat dA. Okay, okay. So now, okay, so this is the one. Okay, this is the first expression you need to consider. Okay, now for simplicity, okay, for simplicity, we can consider, okay, so can you remember that we have, so this is the wire, okay, this is the wire, this is the antenna. Okay, so we have considered an arbitrary point. Okay, so this is the antenna. Okay, wire. Okay, so we have considered arbitrary point. Okay, for the simplicity of calculation, we can fix this in a reference point. If you fix this antenna in a reference point, so it will be easy to do the calculation. Okay, so I fix my antenna. Okay, I fix my antenna here. Okay, I fix my antenna here in the Z axis. Okay, in the Z axis. So I fix my antenna in the Z axis. Okay. So dipole means there should be two poles actually. That is infinitely small dipole. No? Okay. So there should be a two. So you have learned about the balance, no? Balance, balance. Yeah. Yeah. So if you want to uh, feed the signal to the dipole antenna, you have to use a balance. Okay. But here we are not considering those things. Okay. Okay. So so this is the antenna. Okay. So I place the antenna like this. Okay. Like this. Okay. So this is my antenna. Okay. So the length is very small. Okay. And this is Z axis. This is Y axis. And this is X axis. Okay. X axis. Okay. And I consider this length is, I consider the length is L. Okay. So I place it at the middle point, I place at the origin. Okay. So this point will be L minus 2 minus L by 2 divided by 2. And this point will be L by 2. Okay. So this value will be L. Okay. So I have placed in the Z direction. Okay. So there is the current distribution. Okay. R dash. So this R dash happen in the Z direction. Okay. So I can replace this R dash in Z. Okay. So this is the position vector. Okay. Position vector. Now I can replace. Okay. Now I can replace. Okay. Now I can replace this R dash from Z dash. Okay. So this is a position vector. Okay. So I can, so you have a R dash here and you have R dash here. You can, uh, you can, uh, you can convert. You can, so you can now use the position vector Z dash. Okay, is it clear? Now you can use the Z dash. Okay. So So you know that in the Z direction, let's say that we are using our what is called that the unit vector is Z hat. Okay, so this is the unit vector along the Z axis. Okay, okay, and now this R dash is a position vector. No? Okay, so it is at some position. Okay, so now we can write this position R dash as Z dash Z axis. Okay, so this is the length. Okay, and this is the vector, unit vector. Okay, so this is the total vector. Okay, so this is a total position vector. Okay, okay, so this is R dash. Okay, R dash equal to Z dash Z hat. Z hat is a unit vector. Okay, so we can write this because we place our antenna, our antenna. හරි විනාඩියක් දෙකම හරි විනාඩියක් දෙකම අරෝග මචං එක්සෑම් එකට යන්න ඕනේ කියලා. හරි හරිද? ඒකෙන් ඉන්න දෙක පහුවෙන බලන්න කියලා කිව්වා. දෙකම ගන්න නැහැ. මම ඔබට ඔක සෙට් කරන්න. හරි. ඒක නැත්තම් මම සමුදෙනවා. ඔන්න සමුදෙනවා. හරි. anyway ඕනද? මම එක තුන මට තියෙනවා මේකත් මේ ආයෙ ලයිව් එකක් තියෙනවා. එන සඳ බලන්න. එන සඳ කරලා ඔල්ලන්න. Okay. Right. So we can write this like this. Okay. So now we can write. So you know that this I is not a variable. Okay. So this I is not varying. Why I is not varying? Because this is very small, and we consider that I is uniform. Okay. So this I is not varying. Okay. So we can write here R dash equal to mu naught E minus JK R, okay, minus JKR 45R, okay, and so length, now you have to do the length integral now, L, so L is minus L by 2 to plus L by 2, so L by 2 to plus L by 2, okay, and this I is uniform, so you have I, okay, and you can write this as E J K. So this is n hat. Okay, this is n hat. Okay, this is n hat, and you can write this R dash like Z dash Z hat. Okay, Z dash Z hat like this. Okay, and so this will be the. So this is DL. Okay, so you consider the arbitrary value now. Okay, so that is L. You are going to through this line. Okay, now we place this line in Z direction. Okay, so this line is in Z direction. So what is the so this Z del become what? Oh yeah, so we place the antenna, this length, along the Z axis. Okay, so now you have to integrate it from one. This L is in Z axis, minus L to minus L by 2 to L by 2. Okay, so you have to integrate it in what direction? Z direction. Okay, so this will you have to in the Z direction. Okay, okay, so here you have another one, this one. Okay, so I put Z dash. Okay, here is a dash, the Z value as Z dash, so this also should be Z dash. Okay, that is a notation, don't worry. So if you put Z here, you can put the Z here also. Okay, 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 so this is a position. Okay, so I use that position with the magnitude and unit vector. Okay, and you can so the Z, so I put any value at is as Z dash. Okay, so this also should be Z dash. Okay, okay. Because I write this as Z dash, I will write this also as Z dash. Okay, is that clear? Okay, so now you have this one. Okay, and now you have to find this one, n hat z hat. What is the value for n hat z hat? You have to find that one. Okay, so actually I didn't do that part. Okay, I skipped that part. Okay, now at this point, remember that. Okay, maybe you don't, you have learned this one. Okay, you have learned what is called curvilinear. uh, I have actually I have asked from Dr. Who is doing that, Dr. Deepika, no, Dr. Amila, no?
Electromagnetic.
Yeah, she said that she has done these things. Okay, I checked with him. Okay, she said that we had done this curvilinear coordinate system, orthogonal curvilinear coordinate system. Okay, and uh, so uh, so you can find any position vector using the coordinate like this. Okay, and you can you can define the unit vector like this. Okay, and this HU means the magnitude. Okay, and you can find the magnitude like this. So you can find this HU. So you can write your vector like this. Okay, vector like this, derivation actually like this. Okay, then you can get some unit vectors. Okay, for different coordinate system. Okay, unit vectors, and you can find the uh, find the vector when you get the dot product of two unit vectors. Okay, so it is a dot product. Okay, so I will explain it. Maybe you can't understand, but I will explain it here also to get idea. Okay, so here you can see that this n naught and z naught have a dot product. Okay, so n naught is like this. Okay, n naught is this direction. Okay, okay, and z naught is this direction. Okay, z naught is this direction. And if you consider this angle is theta. Okay, what is the so this is z hat. What is n hat dot z hat? What is the value for n hat dot z hat? I have told you this. What is the value? Dot product. What is that?
N into
No, you will get n hat magnitude, z hat magnitude, and cos of this angle. Okay, so you will have cos theta. Can you remember? And what is the magnitude? These are unit vectors. Okay, so what is the magnitude of n hat and z hat? These are unit vector. Unit means one. Okay, so the magnitude is here one. Okay, so you will have n hat z hat equal to cos theta. Okay, and you can use this one, n hat z hat, you can replace with cos theta. Okay. Okay. So here you will have, okay, you will have this one. Okay. AR dash is equal to mu naught e to the power j k r divided by 4 5 r. Okay. Minus L by 2 to plus L by 2. Okay. And you will have, okay. Uh, one thing I forget to tell you that, okay. Okay, one thing I forget to tell you that you can see that this I, okay, this I is in Z direction, no?
Yes.
Okay. I is in Z direction. Um, Yeah. So this I is in Z direction, okay? This I is in Z direction, okay? This I distribution is in Z direction, okay? So I is a vector actually, okay? So you have to, when you are, so I is uniform, but it is a vector, okay? And it is in Z direction, okay? So you have to represent this I as a vector, okay? Not just I, okay? So you have to, the I is in Z direction, okay? So what is the direction? Direction is the Z hat, no? Unit vector, direction, okay? And if you, so I is the magnitude, okay? So if you multiply the I from the direction, so this is a unit vector, and this is the value, okay? If you divide, if you multiply the value with the vector, you can get the current vector, okay? And you can't use I here, actually, you have to use this with the vector, okay? Because these are vector, you also have a direction, okay? This is in Z direction. We assume like this, okay, correct? Is that clear?
Yes.
Maybe you can't understand this 100% correct, okay? But try to understand.
I need to see it again.
Yeah, you need to see it again, okay? So check it, okay? I also take some photos of this note, okay?
So will you
Then
bring
it will
this,
be easy, huh?
will you bring Monday?
Hmm?
Will you bring
Yeah.
I will Monday again.
Okay. Okay. So here you will have Z bar I, okay? Then you have E, J, K, Z dash, cos theta, D Z dash, okay? So you will get this one, okay? Then try to integrate by yourself this one, okay? Try to integrate by this yourself, okay? So I think you can integrate this, okay? Um, um, and also there is another assumption actually, okay? Mm, and that is, okay, and another assumption is there, okay? And you know that this is a L is very small, no?
Yes.
Okay, this L is very small, okay? So, there is assumption that this is, okay, J, K, Z dash cos theta should be equal to 1, okay? Okay, because this L is very small, okay? Uh, yeah, I think you can do that assumption, okay? So first integrate this, okay? First integrate this, and cos theta is a, this Z dash is only the variable, okay? And cos theta is the uh, cos theta is the uh, cos theta is a constant, okay? So you will get some value, okay? You will get some value, and uh, so you know that if you find e to the power 0, it will be equal to 1, okay? So try to, okay? So when you apply, so there is a Z terms, no, Z dash terms. So you are going to do the integration with respect to Z dash, okay? So you have to apply the limits, this L by 2 plus L by 2 to this value, okay? Z dash, okay? Then after you apply the value, okay? After you apply the value, sometime you may understand that because this L is very less, we can approximate these terms to 1. Okay, so we will get e to the power 0 terms approximately. Okay, so so you may have to use this assumption. Okay, L is very low. L is very low. Okay, L is very much less than. It is very um, it is very much less than lambda. Okay, so that means it is very small value. Okay? then you may be able to do this assumption, okay? And try to evaluate this and try to apply this assumption also, okay? And you will get the answer as, okay, answer as z dash mu naught IL divided by 4 5 R e to the power minus jkr. Okay, so this R is the distance. Okay, R is the distance. So you can find this A is varying with respect to distance R. Okay, so different distance has different A. Okay, so using the A, you can find the H field, try to find that one, and you can find the E field, try to find the that one also. And H field you will get this one. Okay, for the H field you will get this one. Okay, okay, no need, try to do this one up to this one, no need to find the H field and E field. Okay, so try to evaluate this integral and do this assumption and try to get this value for the A. Okay, try to get this value as a homework. Okay, so we will continue in next week. Okay, so this kind of things you have to done in the exam. Okay, but don't worry, if you follow the procedure, you can get the marks. Okay, sometimes you may miss, if you have done very small mistake, that can be ignored and you can get the full marks. So don't worry. Okay, because we are not completely do all the things. Okay, from derivation we just skip. Okay, so you may not have the complete idea. Okay, so you can make mistake. Okay, so if the procedure is correct, I can give you the marks. Okay, so try to derive this one by yourself. Okay, and we will meet in next week. Okay, and so if you have any problem, you can ask. Okay.